So, of course, I would like to thank the organizers for inviting me here. And so my talk is the first one that doesn't talk about atoms or nitrogen vacancy centers or something else. I'm going to talk about molecules, but I'm very thankful that pretty much all the concepts that I wanted to introduce have been introduced by the other speakers. So I'll just go a bit into explaining at least at the level of what do I mean by this cooperative. So people have been using cooperative a bit, and of course, one also uses collective. One knows from laser theory that cooperativity, is something that refers to the gain medium in a cavity, right? You can also have the single atom cooperativity, which is the coupling squared over the decay rates of the system. So there's a lot of, this term is used quite a lot for a lot of different things. So what I mean by cooperative, again, is connected to the decay superradiance. They have been introduced in the 1950s. It's not really directly connected to that, so I'll just, again, make a disclaimer. So if I look at the decay superradiance, as it has been initially introduced, is a completely artificial model, right? A bunch of atoms which sit in the same spot, they are excited, you go in the Bloch sphere, and then suddenly the excitation, when it goes down really fast, right? At one point in the beginning, and also this is to respond to a question somebody else asked, for superradiance, you need two particle correlations. So if I take a bunch of excited spins and I let them go down and I try to do some in-field theory, I will never reproduce superradiance. You don't necessarily need to build two particle correlations. So superradiance on the original decay superradiance picture of the Bloch sphere inverted necessarily needs quantum correlations. And some people actually have shown that subradiance might necessarily need three-body correlations in the end. So what do I mean again by, I take this decay model. A decay model is completely artificial. The things are in the same spot. And of course, in reality, we know that if the atoms would go very close to each other, first they would make molecules, so that's not possible. And the second thing, the dipole-dipole shifts would be amazingly high, and that's why you would never realize the original decay model. This could be realized, for example, with a lot of atoms in a cavity if they're positioned at the same spot. But what we mean usually by superradiance is the other kind of superradiance. I mean, it's the same kind of effect, but it's usually treated in sort of a classical way in the single excitation subspace. So the simplest example here is, well, actually now I'm going to a system where I can have up to two excitations. So I take a system which is inverted, and because the two atoms are the two-level electronic systems are very close to each other, they see each other, they modify they modify their electromagnetic vacuum environment, and they start dipole-dipole interacting. So what it means is that an excitation can jump from one atom to the other one and back. On top of this, when they decay, so if one of the atoms wants to decay, it necessarily needs to have some information about the presence of the second atom, right? The second atom just simply modifies the environment. So the typical cooperative behavior usually is that if I look at this system and I look at the optical response, I notice that the system reacts as a hybrid system. So it doesn't react as two independent atoms, which might also be, constructive interference in some direction, but necessarily one has to take into account the interaction between them, and one needs to describe the system in a hybrid way. And now you get this, depending on the symmetry of collective superposition states, you might get states which are superradiant, and you might get states which are subradiant, right? And these are very nice, right? As Derek was already pointing out, subradiance is associated with also quantum metrology, quantum information, and these kind of applications. Good, and now a bit of advertising. So we wrote this PRX quantum tutorial a while ago to point out a few of these applications and the fundamental tools of how to deal with cooperative quantum phenomena in light-matter interactions. And two of the previous speakers already introduced this experiment by Emanuel Bloch, where just putting together a bunch of atoms, you get a cooperative response, so that an atom-thin layer can already produce theoretically 100% reflectivity. So this cooperativity can be taken to applied to the generation of optical metasurfaces. The second thing is that there's the connection condensed matter. This kind of optical metasurfaces also can be, one can do this topological quantum optics approach on. So these are good platforms for excitation transfer, controlling excitation transfer, and so on. But now, so this is all I had to do with atoms, two-level system, electronic systems. Now I want to bring the problem towards a more complex ground and sort of also introduce what Vahid Sanduktar probably will talk the next days. Before decay superradiance or before any kind of cooperative behavior, this kind of cooperative or this kind of superradiant or collective states have already been observed actually in molecular aggregates in the 1930s. And there are these two observations by Jelly and Scheibe of some sort of dyes where monomers have been aggregated in structures which contain a few tens or maybe hundreds of monomers, where the whole thing posed an absorption which was much higher than expected. And the theory for this has been kind of based on Kasha's theory from the 1950s, so the same time as decay superradiance. And actually, this is simply the same thing as the one excitation superradiant state. So it turns out that if you look at these monomers, so the monomer is just individual molecules with some dipole, transition dipole moment oriented in some direction. Normally, before aggregation, they just point in all the possible directions. So the absorption is just the absorption of a single monomer times the whatever number of monomers you have. But upon aggregation, which could be something like you put these molecules in some solution, and because of van der Waals interactions, they might start orienting themselves. And after they reach, after they are frozen, they can aggregate in this kind of situations. And this is what, when you think about atomic arrays and you look at the collective states, you always assume that the transition dipole moments are pointing in some direction. And if they're pointing like this or like that, there's a very different kind of interaction because the shifts of collective states can go up or down depending on the orientation. So there are two different kind of, there are a few different kind of molecular aggregates, but two fundamental differences are H and J aggregates. They both show this increased absorption. One of them is much more resilient than the other one. Good. Then this is something that I will go towards the end of my talk to show how you apply open system dynamics or quantum optics methods to describe these kind of molecular systems. Now, and also, as another speaker already pointed out before me, that if you look at the experiments in cavities, then you can really look for modification of material properties. So there's a new direction for, let's say, 10, 15 years that is pointing out towards throw everything in a cavity that has a mechanical, optical, chemical property, and then see what happens. And if you cannot have good cavities, make bad cavities and still put a lot of particles, just an Avogadro number. Right? And there's a new direction of going towards chemical reaction modifications, phase transitions, and everything else. So I'd like also to point out why. So there are, let's say, from my point of view, at least two different kind of experiments with molecules. One of them is at the level of very nice controllable systems where you put a single molecule in some host matrix, a molecule which is not chemically reactive, a molecule that can be really nicely played with. They have very nice properties, right? You can synthesize them nicely. They are well isolated. And they have the promise of, either, they are good single photon sources. They are good nonlinear elements. They are transducers of force, pressure, and everything else. I just put here one reference from Vahid Sanduktar group where they show how to turn a molecule actually into a good qubit, so into a good close two-level system. But mostly I focus on this other kind of experiments, which are experiments where you put a lot of molecules inside a cavity. Each of these molecules are, they are picked because they have amazingly large dipole moments. They might be kind of dirty because they react to stuff, or they don't have such a good quantum, what is called quantum efficiency of fluorescence. So if you pull light, mostly there's going to be some non-radiative transitions, but sometimes you get some fluorescence. But with these ones, you can observe some nice stuff. And these are, I refer to two experiments, where one of them shows the modification of the photochemical reaction rate in the presence of an optical cavity. So you can modify reaction landscapes by just exposing your molecule to an optical confined cavity field. So these are things which actually appear in the vacuum, meaning that you don't need to drive it with photons in order to modify the chemical reaction. You just modify the potential landscapes. The second one also refers to a slightly different property, is the electrical conductivity. So if you put leads onto one of these organic semiconductors and you put it close to a plasmonic waveguide or the plasmonic surface, then you can see that the mobility of the carrier seems to be enhanced. Good. So now I go to the quantum optics part. Now it's just sort of motivation and jumping from quantum, from atoms to molecules. And I would like to point out this is definitely not a model of molecules. People have used a lot of two-level electronic system descriptions to show properties of transport, of excitations, or charge, or anything else. This is usually pretty bad model. So a molecule necessarily needs this potential landscape complexity. So in a molecule, and just think about the simplest kind of molecules, diatomic molecule where the nuclei vibrate, and then for each position where, for each separation of the nuclei, you have to recompute the electronic orbitals. So electronic orbitals look like this, they're not flat, right? For an atom, if I move it around and I look at the center of mass, the orbitals look exactly the same no matter what the center of mass is. For the molecule, the relative motion dictates how the electronic orbital looks like. So I put this nice, very, picture of the complexity of the molecules as this, this can make somebody completely confused. And I point out that my direction of research basically refers very much to this picture. So if I look at a single molecule and I say this is just a two-level system, then I consider this S0 to S1 transition. So this is the ground state, this is the first electronic state. In reality, in experiments with molecules, when you put some light on it, you go from the S0 to S2, and then you have a process of internal conversion, oftentimes. On the other hand, you also have other processes like vibration relaxation. So once you couple to the electronic degree of freedom, so you imagine the electronic orbital, necessarily couples to the vibration of the nuclei. And this vibration of the nuclei, oftentimes, because you're in solid state, in a host matrix, or even in a solvent, these vibrations decay pretty fast. And this is pretty bad for anytime you want to do something coherent. On top of this, you also have intersystem crossing because you might have more than one electron. So you are thinking about the electron that you excite, but this electron could flip, and then it cannot go down because of Pauli exclusion principle. So it has to perform an intersystem crossing and to go to a state which is basically very long-lived, which is a phosphorescent state. Right? So maybe by now I'm convinced that there's a lot of effects that can happen with the molecule. And this is basically what my group is kind of doing at the moment, modeling different detrimental effects. So why would you care about these things? Is because a lot of these experiments, a lot of photophysics, photochemistry, charge or excitant transport experiments are based on exciting this electronic transition. So they are basically fundamentally strongly modified by vibrations. Good. So now let me just slowly show you, and very quickly show you how we build a model for this. So imagine again the simplest kind of molecule, a hydrogen molecule, and you can plot the potential landscape for the ground and the excited state along a nuclear coordinate, and the nuclear coordinate is just simply the relative separation of the two nuclei. And if you expand the molecular potential landscapes along this nuclear coordinate, if you take a harmonic approximation, you look at the difference between the two electronic landscapes, the two potential landscapes, and you see that there's a difference in the minimum. And what this difference means is that if my electron is in the ground state, then the nuclei are at some distance of 3 angstrom, for example. If now the electron is going to the excited state, maybe the shape is a bit different, so the nuclei can go a bit farther away to reach equilibrium. And this is what gives rise to this electron-vibron coupling in this case. So here I just do a simple, this is your two-level system. Sigma dagger sigma means that the projector operator for the excited state. You expand the ground and excited state potentials. P is for the momentum of the nuclei, for the relative motion of the nuclei. And if you do the math, which is straightforward, you find something which is, these are the vibrations of the system, so the nuclei. This is the electronic degree of freedom, so this would be my two-level system in the absence of any coupling to the vibrations. And this is what is called a Juan-Rees factor. And for anybody in optomechanics, you recognize that this is just the radiation pressure Hamiltonian, but with spins instead of bosons. Right? So instead of A dagger A, which you would have for optomechanics, you have a sigma dagger sigma. And you see that this thing, if you, for example, you take an exponential of it, this is just a conditional displacement operator, right? From quantum optics, you know that E to any kind of displacement, B plus B dagger gives you a displacement to a coherent state. And this is just a conditional coherent state displacement. So this is the only slide that I have with equations, just to point out the method. So again, the method is very similar to what one would do in optomechanics for the single phonon strong coupling optomechanics. You look at the system where you look at vibration, the evolution of, so equation of motion for vibrations, and equation of motion for a polaron operator, which is the electron dressed by the nuclear cloud. So here, this method, so this quantum Langevin equations can include also a thermal reservoir. So we can include vibrations which are thermally excited. You can also include driving with a laser frequency, also the input noise associated with spontaneous emission. And one can find the formal solution. From this formal solution, one can follow the standard quantum optics techniques to calculate two particle correlations and calculate spectra and everything else. So now, for the last part of my talk, I go towards the results, and I like to discuss a bit the physics of it. So applying these kind of methods, we looked at a few things. So just to justify the first work that we did, if you look at cavity QED, and this has already been introduced before, you are looking at concepts such as polaritons and vacuum Rabi splitting. So if I take a two-level system and I put it in a cavity, and I go to the strong coupling regime, I see that there are two polaritons, right, which are hybrid light matter states. Now, these two polaritons come as eigenstates of the system, which is perfectly diagonalizable. Now, what vibrations do when you put a molecule inside the cavity, vibrations destroy this eigenstate, so it can couple these two eigenstates. So one can show immediately that a molecule in the cavity can already, can give rise to polaritons which are talking to each other. So typically, for molecular experiments, you're always going to observe polaritons which are not balanced. If you go into the strong, into the Purcell regime of this cavity QED, you can also show exactly what experimentally has been shown of turning a molecule into a single closed qubit by enhancing a lot the radiative decay rate, the spontaneous emission rate of the system, and a few other things connected more to the chemistry. Now, the second thing is that this quantum Langevin approach also allowed us to look at systems where you have molecules inside host matrices where phonons are present as well, so inside the atomic or molecular crystals. So this is a pretty powerful method to treat any of these kind of systems. But now I would like to focus on what I mentioned already from the beginning, into a very nice system where whatever people are talking in quantum optics in terms of atomic arrays or anything else is already sort of present. And I don't know how many of you are aware of this, so the whole history of molecular aggregates. But this has been since so again, as I mentioned, since the 50s or 60s, it's been kind of known that dipole-dipole interaction in these molecular aggregates are very strong because the distances between monomers are the order of 2 or up to 10 nanometers. So these systems exhibit a lot of collective states. And if you look at the Venn diagram, the collective state, which is perfectly symmetric, where light actually usually couples to, right? Because these systems are so small, then for light impinging at a wavelength of 1 micron, they are basically in the same spot. So if you address these systems with constant illumination, for a given orientation of the transition dipole moments, you're going to typically go exactly on top of this Venn diagram. And this is the symmetric state, which is also super radiant. So for this kind of what is called H aggregates, when you are photo-exciting it, you are going to this state. And this state, in principle, is orthogonal to all the other states, especially to the states which lie at the bottom of this diagram, where states which are subradiant appear. Now, what happens is that the fact that vibrations are present in the system, then states of symmetric character are going to be very strongly coupled to states with asymmetric character. So in a typical pump experiment for this, you put light into this state, which immediately goes down to the bottom of the hill. And this is known in quantum chemistry and molecular dynamics and everything else as Kasha's rule, which basically whatever is up goes down in more, in more fancy terms. So we have been shown that if you are, if you're looking at the coupling in the collective basis, the coupling of the symmetric state, which is superradiant, with subradiant states, we basically can show that a couple of rate equations, one can make rate equations where the symmetric state is going to go towards the bottom of the hill at a rate which here we call this kappa s, which can be computed analytically, and under some assumptions that a number of vibrational modes are available for the molecule. And what I mean by a number of vibrational modes, these molecules are usually pretty big. They have a lot of atoms. So there's 3n-5 possible vibrations of the nuclei. And if you have some low-lying vibrational modes, then the energy from this to here can be dissipated into these modes as long as these modes are smaller than the 4 times the dipole-dipole coupling of nearest neighbors. So we've been able to get some scaling, which surprisingly, maybe surprising, maybe not surprisingly, kind of fit the exact numerics. And one can see that basically this, this Kasha rule is proportional to the dipole-dipole interaction between nearest neighbors. So it depends very much on the monomer, also orientation and separation, and also the number of available modes. And now this is my last slide, so I can jump a bit more. So the purpose of all our theories is to go towards mesoscopic ensembles. So to describe what happens, starting with the electron-photon interaction in the presence of vibrance, to describe what happens when you have mesoscopic ensembles where a lot of stuff happens. So there you have inhomogeneous broadening, you have frequency disorder and also positioning disorder, you have dipole-dipole coupling. So all these things are pretty much numerically kind of impossible to deal with. So what I did was looking at the theory where for any kind of ensemble of molecules inside a cavity, because of this big inhomogeneous broadening, molecules which are close to each other will be very different in frequency, so they kind of look like donor and acceptor. What it means is that a molecule which is broadened, or a molecule which is disordered has a higher frequency, could actually lose the excitation to a molecule which has a smaller frequency, right? Because you put them together, you have a dipole-dipole coupling, and then on top of this, you have some vibrational relaxation where you can go from some vibrational level to a bit down. This is known as the Foerster resonance excitation process, the transfer. This is the basic of our model, and the story short, we showed that the vacuum Rabi splitting for a disordered mesoscopic ensemble of molecules saturates at one point, so it doesn't follow the square root of n, right? And I've seen previously also in Toabro's talk that there's also a scaling like that. So it saturates at one point, and it can even go down with the number of particles. So the question is, if you throw a bunch of molecules, and probably this is going to be valid for other systems, that where the electron can also interact with some phonon or vibron, if you throw a bunch of molecules, it's pretty hard to figure out what is the effective number of molecules that you have in there. And at one point, it doesn't really help increasing the density because you're going to run into these kind of troubles. So with this, I'm done, and thank you very much for your attention.